All right, so let's talk about mathematical induction. So in general, when we want to prove some formula for using mathematical induction, we're basically trying to use induction to prove that an assertion that Pn is true for all n in n, where Pn is a propositional function. So usually when it comes to a proof by induction, it has two parts to it. So the first part, usually called the base case or the basis step. So usually whenever we want to prove something that where n is a positive integer, then we want to show that p of 1 is true. So once we have shown that p1 is true, we move on to the second step. So this is called our inductive step then. So what our inductive step tells us is that, well, we have to assume that for every positive integer k, that if we assume that the propositional function at k is true, then it has to be true that the kth plus one um, propositional function is also true. So those are the two steps that we had to do to show prove a statement using mathematical induction. So I have a template prepared to for us to use to prove statements using mathematical induction. So let's go through those. Um, so usually it has 7 steps, but usually you can compress these statements into maybe less than a few steps. But so usually in the first step, so let's say we're given a statement. So the first step is to express the statement that is to be proved in the form for all n uh, greater or equal to b, where n is a positive integer, that Pn is true. Now b here is a fixed positive integer, not positive, but it could be any integer. But yeah, if you have b here, so that's usually your starting point here. Now, if it says, for example, for all n in n, where n is a natural number, then Pn, so usually we would let b be equal to 1. And for statements that say something like, well, for p of n, for every non-negative integer n, so that means we let b equal to 0. So that's the first step. We want to express the statement that is to be proved. Um, so now the second step here is to write out the basis step. Um, so usually the basis step is the starting value that you're trying to prove. So for example, if I'm considering for all n and n, p of n, so then in that case, we want to show that p of 1 is true. So usually in general, if b is an integer, then we would have to show that p of b is true. So make sure we're using the correct value of b. And once we have shown that the base case is true, then we are done the first part of the proof. So we're good here. So the third step here involves us to write out the inductive hypothesis first. So we have the inductive step. So this is our second part of the proof. Now we want to clearly identify the inductive hypothesis of the form. So usually it's of the form assume that pk is true for every integer k greater or equal to b, where k is an integer here. So that's what we need to say. So that's the thing that we're trying to assume in order to prove the next step. So that's the third step. Now the fourth step here is the state what needs to be proved. So what we want to prove in our case, inductive step, is that the kth plus 1 step is also true. So pk plus 1, p of k plus 1 is also true. It's pretty helpful to know what it says. So that way you could reach that target that you want to end up with. And then step 5, you just need to prove that p of k plus 1 is true, but you need to make sure that you guys are using the assumption that p of k is true. So that is the important part of mathematical induction. You need to be able to use your inductive hypothesis in order to prove that the p of k plus 1 is true. Now, for the sixth step, we need to basically identify the conclusion of the inductive step by just simply saying this completes the proof of the inductive step. And the last step for step 7 is just to conclude the proof that you're proving. So we're saying by mathematical induction, P of n is true for all integers n with n greater or equal to b. So that's the 7 steps of mathematical induction, and we'll try to follow this when proving the following statements. So we'll go have a look at some examples um, about mathematical induction. So the first example that we'll have a look at is that to show that if n is a positive integer or natural number, then we have the sum of the natural numbers. So we have 1 plus 2 plus 3 plus so on all the way to n. So the sum of n natural numbers is equal to n times n plus 1 divided by 2. So we first usually write the proof down. So proof. So what is going to be our Pn in this case? Well, our Pn is going to be the proposition that the sum of the first n positive integers is equal to n times n plus 1 divided by 2. So let Pn be the statement. So usually I'm going to use the colon equal sign to denote the what is being told. So we're saying that the sum of the first n positive integers is equal to n times n plus 1 divided by 2. So that's our proposition. So we have to be a little bit clear. So where n is a natural number or a positive integer. Okay, so we need to do 2 things. So first step, so we did step 1. Now, according to the template here, we need to do our basis step. So we write down the base case. And because n starts at 1, we need to show that P of 1 is true. Because n is starting at 1. So usually when we see this symbol, we mean that, well, n is equal to 1, 2, and so on. So the first value that you want to use is n, or 1. Okay, so we want to show that P of 1 is true. So what does P of 1 mean? Well, P of 1 is the statement that, well, if we consider the left-hand side, so we're only considering the first value of the sum. So the left-hand side is going to be 1. But on the right-hand side, if we put in n is equal to 1, this would give us 1 times 1 plus 1 divided by 2. And this is equal to 1 times 2 divided by 2, which then ends up with 1. So therefore, the base case has been proven. Okay, so that's the base case. So now we need to move on to the inductive step now. So this is called our inductive step. And what that says is, well, we need to assume, first of all, so assume that for all k in n, that P of k is true. I.e., so what does P of k mean? So it's important to write down what P of k means. So this is our inductive hypothesis, which I'll denote by IH. What that means is that if we take the sum of the first k natural numbers all the way to k, this is going to be equal to k times k plus 1 divided by 2. So that's our inductive hypothesis. This is the assumption that we're trying to make that is true. So we need to show, so what's our next thing that we need to show? To show that, well, we have to show that the p of k plus 1 is true. Now, what is the goal that we're trying to show? Well, if we write this out, well, p of k plus 1 means that, well, if we take the first k plus 1, the sum of them, all the way to k plus 1, this would be equal to k. So instead of k, we put k plus 1. So this would be k plus 1 plus 1, and then all this divided by 2. So that is the goal that we want to show, obtain in the end. So this is our goal. So in order to do so, we had to do a following step. So indeed, now let's work with the left-hand side first. So in this case, so the inductive step at this point is where you have to do a little bit of algebraic work. So first of all, note that we could write this in this way. So we're taking the first k. Now, what does our inductive hypothesis mean? Because by assumption, we're assuming that pk is true. So what that means is that this statement we're assuming to be true. So what we have to do now is use this assumption and put it into our next step. So what we're doing here, by the inductive step, what is this equal to? Well, this precisely equal to this. So this is exactly k plus 1 divided by 2. So I'm going to put that in. So now what we're ending up with is k times k plus 1 divided by 2 plus, now we still have the k plus 1 term on the outside. We're not done with this term. This is the thing that we still need to use. So now we just have to simplify things. So first of all, observe that we could find a common denominator. This is 2 times k plus 1. And all this now is divided by 2. Now, remember, so using some grouping techniques of factoring, we could take these terms and put them as one term together. So what we would have is k plus 1 as one of the terms. And what we also have is the outside terms. So we also have the k and the 2. So we're going to join those together and make it into a new term. So that's going to be k plus 2. And all that is divided by 2. Now, are we done here? Yes. So we actually wanted to obtain our goal because technically speaking, this term over here is k plus 2. So we have finished using mathematical, and we proved the inductive step here. So what we have to say now is, so this completes the inductive step. And therefore, by mathematical induction, well, what is Pn again? So Pn, what we said was, well, 1 plus 2 goes all the way to n. This is equal to n times n plus 1 divided by 2 is true for every n in n. And there we go. That completes the proof for this inductive step. So hopefully by now you get the general structure of mathematical induction. So let's quickly recap of what we did. So we first stated what P of n was. So what is our propositional function that we're trying to prove in this case? Then we need to prove the base case. So usually it's the first value that you want to prove to be true. So in our case, P of 1, because 1 is our starting value, we want to show that, well, P of 1 is true. And then now we move on to the inductive step. So we're assuming that, well, PK is true. So PK, meaning this entire statement here. So that is what we're assuming to be true. And because using that, we could show that P of K plus 1 is true. So what that means is that this happens. So that is our goal that we wanted to prove. So now from this step here, we just had to do a little bit of work in order to obtain the desired formula um, in order to complete the inductive step. So, and therefore by mathematical induction, we have proved the statement for all n positive integer. Okay, so that's the first example. Now I have another example, or plenty of examples here. So this one's it's a similar type of question, but this time we're gonna use mathematical induction to show that this statement is true. So now this time is a little bit different because now we're dealing with non-negative integers n. So that's saying starting from 0, 1, 2, and so on. So let's prove this. So, so the first thing that we're going to let is, so we're going to let P of n be the propositional function that, well, 1 plus 2 plus 2 squared all the way 2 to the n, this is equal to 2 to the n plus 1 minus 1, where n is a non-negative integer. Okay, so first we proved the base case. So similar as what we did in the first proof, we need to show that, well, in our case this time, P of 0 is true because 0 is our starting value. So we need to show that P of 0 is true. Okay, so what P of 0 means is that, well, on the left-hand side, we would just have 2 to the power of 0, which is equal to 1, which is true. And on the right-hand side, we also have that, well, 2 to the 0 plus 1 minus 1, that's equal to 2 to the power of 1 minus 1. That's equal to 2 minus 1, which is equal to 1. So because we have shown that they're both equal, so it's 1 equal to 1 in this case, so thereby completing the basis step, or the base case for P of n. Okay, so that's the base case. Now we need to prove the inductive step. So the inductive step says we assume that for all k for 0, where k is an integer, that pk is true, i.e., so what that means, pk 1 plus 2, 2 squared, all the way to 2 to the k. This is equal to 2 to the k plus 1 minus 1. So that's what we're assuming. So this is our inductive hypothesis. So now we want to show that P of k plus 1 is true. So what does that mean? K plus 1. So this is 1, 2, 2 squared, so on until 2k plus 1. This is equal to 2 of k plus 1 plus 1 minus 1. So this is our goal. Okay, so indeed, let's work with the left-hand side. So what we have is that 1 plus 2, 2 squared. I'm going to rewrite this until we reach the 2 to the k, and then 2 to the k plus 1. This is equal to, well, here, by the inductive hypothesis, so we're going to use this fact now. So this here, up to here, this is equal to 2 to the k plus 1 minus 1. Okay, so this becomes minus 1 and then plus 2k plus 1. Okay, so now we could actually common factor out the 2 to the k plus 1 so that we have two of them to the power k plus 1 minus 1. But note that I could write this as 2 to the 1, 2 to the k plus 1 minus 1. And because we have multiplication of the same base, we just need to add the exponents. So that ends up being 2 minus 1. So that's it. So this completes the inductive step. So therefore, by mathematical induction, we have shown that P of n, which is defined as 1 plus 2, 2 squared, so on, 2 to the n. This is 2 to the n plus 1 minus 1 is true for all non-negative integers n. So that's going to be it for the first part of this mathematical induction. So there's going to be more examples coming later on. So be sure to check out that later on.